Hello, and welcome back to Mr. Powers Teaches Algebra. Today we're going to talk a little bit about simplified radical form, or simplifying radicals. All right, so let's talk about that. Okay, we're doing these roots, these fifth roots, fourth roots, nth roots. What do we mean? So when we talk about simplified radical form, right? Uh, we're saying we want it in a certain way. We want it to look nice. That's kind of what we're saying. So what does that mean? These four rules right here. All exponents in the radicand must be less than the index. Okay, so the radicand, so this is the radicand. So anything in there, okay, must be less than the index. So the index is here, and then the powers are in here. So like this. So the power of the index, the exponents in here less than. So m's less than n. Any exponents in the radicand can have no factors in common. So, you know, if you wrote this as a fraction, right, this actually is the same as x to the m over n. This m over n must be a reduced fraction is another way to think about that. That's number 2. 3, no fractions appear under a radical. Okay, so we don't want any fractions in here. And no radicals appear in the denominator of a fraction. Okay, so that's easy enough. Let's do a couple examples. All right, so the first one I think we'll do is y to the 7th. Y to the 7th. And we're going to do the square root of y to the 7th. Okay, so let's reduce this. We're going to follow those rules that we talked about. And if we need to make a little note here, the square root, right, we pretend there's a 2 there. So we want to reduce this as much as possible. And we're going to use this little property that we have. And that is that if I have a y squared underneath a square root, that is the same as just a y. And that's our goal, is to get as much out of the square root as possible. Most of the time, that's all we got to really worry about is what can I take out of the square root? Right? And so I want to rewrite this y to the 7th as a bunch of y squareds, as many as I can. So I can say it's y squared times y squared times y squared times y. And I've talked about this a little bit before, so I'm tempted to just skip to these shortcuts that I've mentioned. So I'll mention the shortcut one more time. Well, how many y squareds could I get under here? Since I have a square root, I want to get y squareds. How many? Well, there were 7 y's underneath the radical. I can get groups of 2. There's 3 groups of 2. So I can, each one of those. Now, if I want to be really specific, actually, let me go ahead and rewrite this like this. Square root of y squared times square root of y squared times the square root of y squared times the square root of y. Because I have a property that lets me do this, right? That's this property. The square root of x times the square root of y is the square root of xy. Of course, I'm going the other way there, but I have that property. And now each of these is a y. So I have y times y times y. And you can see how I can kind of just, I could have taken this and gone straight to here pretty quickly. It's like the 1, 2, 3, I got 3 y squareds, there they are, times this root y. I still have 1 y underneath the root I can't take out. And so what do we get? We get y times y times y is y cubed. And I got 1 y still left under the root. This would be my simplified radical. And so remember what my trick is. You got power of 7 under a square root, and we're trying to reduce it. It is the same as 7 divided by 2. So here's another example where we can see that. Where's the button? There it is. So if I did that little division problem off to the side here, I say, hey, 7 divided by 2, what do you get? You get 3 remainder 1. That is 3 outside the root, right there, and 1 inside the root. And that's a trick I'm going to keep using, especially on these next few examples, because it's way faster than trying to break up the product into factors with that power, right? If I have a cube root of cubes, if I have a fourth root of fourths underneath the radical, rather than do that over and over again, realize I have this pattern, I'm going to use it. So I got, let's go ahead and do a more complicated one like this, where I get to use that trick a little bit more. So another example would be this. Let's say we have the square root, or actually, let's do the fourth root of 32 x to the 9th, y to the 5th, z to the 12th. Okay, and I'm going to do this in one step, because I am Mr. Powers and I am amazing. So I'm going to do these each separately. All right, so I'm going to have a number, maybe a power of x, power of y, power of z outside the root. So that's going to be out front. And then I'm going to have the fourth root. I'm going to have stuff under the fourth root. So what's out front? Well, first, let's take care of the 32. There's my factor in the root. Do I know the fourth root of 32? I don't know. Let me see here. 2 cubed is 8. 2 to the 4th is 16. 2 to the 5th is 32. So actually what I could do is just realize that this 32 is really 2 to the 5th. And I can treat it like that. So what's 5 divided by 4? It's 1. Let's see. It's 1. So I'm going to have, it's 1 remainder 1. 5 divided by 4 is 1 remainder 1. So 1, 2 outside the root, 1, 2 inside the root. Now my x's. I'm going to have x. How many x's? What's 9 divided by 4? It's 2, remainder 1. So 2x is outside the root, 1x inside the root. What's 5 divided by 4? We did that. 5 divided by 4, we already did that one. That's 1 remainder 1. So 5 divided by 4, I'm going to say that's 1 remainder 1. So 1y outside the root, 1y inside the root, and then to the z's. 12 divided by 4 is straight up 3, no remainder. So I'm going to have z cubed outside the root and no z's inside the root. And I am done. That's my quick shortcut way of doing that. All right, just really quick if you need to see. For the x's, 9 divided by 4 was 2 remainder 1. So 2 times 4 is 8 remainder 1. So that's why we had 2 x's outside, 1 x inside the root. There's my shortcut. I like doing it that way. It's just too easy. Got to do it. And that was z cubed. Oops. Z cubed. I just want to make that cubed a little nicer. There we go. Okay. So, one more example, and I'm going to end this video. I know it's already getting up to 10 minutes, but there's another kind of example we definitely want to see on these. And then I'll do a video on seeing if we can do technology on these. Actually, I've already done a video for technology on these, so I think we're going to be okay without that. We'll use the same one as before. So, one more we need to do is this. The 9th root of x to the 6th. We must do this. Now, this time, okay, 6 divided by 9, we can't do it, right? So what's wrong with this? We got to check, well, like I can't take any x's out, but this is not reduced. I'm going to tell you that right away. It's not reduced, and it's because of, I think, that rule 2. All exponents in a radicand can have no factors in common with the index. In other words, if I write a fractional exponent, it's got to be reduced. So if I rewrote this as a fractional exponent, which is my method, this is the way I like to do it, this would be x to the 6/9. And that 6/9 is definitely not reduced. There's definitely, I can reduce this fraction. I can divide the top and bottom by 2. So 6 divided by 2 is 3. 9 divided by 2, I can't do that. What am I thinking? They're both divisible by 3. Let's try that. 6 divided by 3 is 2. 9 divided by 3 is 3. There. That's reduced. Now let's rewrite that. It's going to be the cube root of x squared. And I'm just using that property once again. What property I use there is this one, x to the m over n. I can write as the nth root of x to the m, or you could write it as the nth root of x, all raised to the m. I went with this one, though. Okay, there you go. Piece of cake. That is it. So I just wanted to show you guys a few examples there, reducing radicals, and use my trick. I hope that was helpful. Until next time, enjoy doing math.